Hello students, welcome to the class. So today we will see the theory part 7 of the chapter 6 equilibrium, in which we will be covering section 6.9 to 6.10. So this is the disclaimer. Our objective would be to look at the classification of substances as acids and bases. Now this classification will be based on three theories: Arrhenius, Bronsted-Lowry and Lewis concepts. I will look onto Lewis concept. We'll look onto each of them one by one and see that how we can compare. So at the same time, we'll compare also the acids and bases based on these concepts. If I talk about the specific sections of the NCERT, then first we will cover the section 6.9 ionic equilibrium in solution, in which we will next see acid, base and salts. After that, in acid, base and salts, we will see the Arrhenius concept of acid and bases, then the Bronsted-Lowry acids and bases, and the third one, the Lewis acid and bases. So all of these three concepts are based on different criteria for acidic and basic nature. So they have different terminologies, as well as you can see that each of them can be characterized also by different or same examples. So both can be the case. So there may be a case that the acid cannot be explained on the basis of one of these definitions, so you have to look upon the other. Now, after getting all of this, we will move on to the NCERT problem 6.14 and 6.15. So first, let us try to understand what is dissociation of electrolytes. Now, in an ionic equilibrium, if I define, then it is a state where the dissociation of an electrolyte into ions in a solution is equals to the rate of ion recombination. So you can say in a way that the number of ion is conserved in a solution. Then you say that, okay, now we have the stage of ionic equilibrium. So that would also be represented as a constant concentration of the following ionic species present in a given solution. Moving on to the next part, which is electrolytes. Now, if you know that what is ionic equilibrium, then you have to understand that what is dissociation, because we said that, okay, now you have to dissociate, and then at the part where your dissociation and your association are same, you tell that part as ionic equilibrium. Now the second part is that on what basis we decide that how much dissociation will occur, or the extent of dissociation is dependent upon what factors. So one of those factors is electrolytes. So basically, we will try to define the dissociation on the basis of the nature of the substance in which we are interested in. Now those substances are classified as electrolytes. And what is the result of this dissociation? That the solution that is formed in which your electrolytes is dissolved has a conducting property. It can conduct electricity, and that conductance or the conduction is due to the ions present after the dissociation part. Now, as I said, you need to know the extent of dissociation. Now, on this basis, we have two categorization. First is strong electrolytes. Strong are one which ionizes completely into the solution. So as long as your electrolyte is soluble in water, it will dissociate completely. So we will not consider those electrolytes that are not soluble in water. Suppose you can dissolve only 5 grams of salt in a given amount of water. Then the salt will be considered as strong electrolyte. Suppose if you added the 6th gram, then in that case you will say that, okay, this one is not getting dissociated. But the point is that it should dissolve. Then and then only we will try to define its half dissociation or full, I will not say half, small dissociation or complete dissociation. Here are some examples of strong electrolytes. So first is strong acid, strong bases and salts. So all of these three are always strong electrolytes. So this is a very important thing to remember. All strong acids, all strong bases and salts. So salt has no characterization as strong or weak. So all salts are strong electrolytes. And how do they dissociate? Suppose we take the example of a strong acid named hydrochloric acid as HCl. This HCl, when it is dissolved in water, it dissociates into two ions, cation, which is H plus, and the anion, which is Cl minus. Now here is a very important point. In some cases, you will see H3O plus rather than H plus. So they both are resembling the same thing. The only part is that after dissociation, you get the H plus, but it does not exist for a long time. As soon as the water comes in contact with this ion, it hydrates it to form the H3O plus. Got it? We will see the well-defined reaction when we'll move to the reaction with the water. Here also water is present, but we have to show the exact dissociated ion, so we have taken it as H plus rather than the final one. Similarly, what are weak electrolytes? So these are electrolytes which ionizes only partially. Means if you are suppose 2 moles of the electrolyte is soluble in your solution, then out of the 2 moles, only 1 or only 1.8, so either can be the case, but the whole part will not get dissociated. Clear? Now, the equilibrium is established between the ion and an unionized molecule. So this ionic equilibrium is more validated for weak electrolyte, because for strong electrolyte, we don't have any such situation. Now you can call the final dissolution, or you can say that the final dissociation of strong electrolyte as your equilibrium position after all of the strong electrolytes is dissociated. But see, there is no point in looking onto that. The equilibrium is playing a much more important part in this weak electrolyte, where there is a tug of war between the two parts, which is ionized and the unionized part. Got it? So let us resemble the same with the help of an example. Suppose we are taking acetic acid. So this is a weak acid. Remember, only 3 things are taken as strong electrolytes in case of ionic equilibrium: strong acid, strong base, and salts. Since acetic acid is a weak one, it will be a weak electrolyte. And when this thing is dissociated with water, then it forms H3O plus. See, in this case, we have taken the hydrated H plus ion, which is H3O plus rather than the normal H plus. Now both of these equations are correct, but the more appropriate representation would be the second one. So if you can write HCl plus H2O giving us H3O plus Cl minus, then that would be more suitable. Here you can also see a difference in the arrows. In the case of strong electrolyte, you have a single headed arrow, whereas in the case of the weak electrolyte, you have a harpooned arrow. Harpoon means you can see that the upper part is moving on to the right, whereas the lower part is moving on to the left. So they are 2 hooked arrows oriented in opposite directions. This is indicating that your whole part of reactants is not getting converted into product, but there is a stage of equilibrium between the reactants and products, or you can say between the ionized, which is on the product side, and the unionized, which is the reactant side. Opposite to that, the strong electrolyte have a complete dissociation. So you can just see it with the help of a single right arrow, which is indicating that reaction is only going in the forward direction and there is no backward dissociation. Is it clear? So this is very important to understand this part. Then and then only you will get the idea of the whole ionic equilibrium. So next is acid and bases categorization. So there are basically 4 categorization of this acids and bases. The first one is the classical definition of acids and bases. The second one is Arrhenius concept of the acid and bases. Third is Bronsted-Lowry acids and bases. Fourth is the Lewis acid and bases. So we have seen these 3 concepts, means we have looked upon these 3 names. We have not discussed in the detail, but this same will give you the types of acids and bases as well. There is one more addition. If you see, there is a classical definition also. We'll look on to that. So first, let us see onto the classical concept of acid and base. How do we derive it? It's very simple. So acids is derived from a Latin word acidus, meaning sour. So if they taste sour, if the substance that you are given with, if it is tasting sour, then you tell it as acids. What is the second characteristic that it will show? It would be the conversion of the blue litmus to red. Third thing is, it will produce hydrogen gas on reacting with metals. So this is also a categorization for the understanding of metal. So whenever you react a metal with an acid, it gets converted into a corrosion form, okay, and it releases hydrogen gas. So this is a very reactive reaction. Similarly, if I talk about the base, then base turns the red litmus blue. Opposite to that, it will turn your red litmus to blue. Further, it will taste bitter. Third thing, it will have a soapy feel. So this is a general physical appearance that we are discussing. So it is soapy to touch. If you touch it, it will feel like a soap. Now this can be well described in this image. If you see on the left hand side, then we have taken an acid in a beaker. If we dip a blue litmus paper into this acid beaker, then we see that the part which is dipped in the liquid is converted into red. Similarly, on the right hand side, if you take a red litmus and dip it into the solution of base, then the dipped part of the litmus paper converts into the blue part, right? Next is the salt. So we have seen what is acid and base on the basis of classical justification. Now we'll move on to the salt. How is salt formed? So it is formed by the aggregation of positively charged ions and the negatively charged ions, which is cations and anions. And where are this coming from? If you look at the salt, then you will realize that the negative and positive part is coming from acid and base. See, we have NaCl, Na2SO4 and K2SO4. Just think about it. What can be the acids or bases that should be constituting these three salts? So if you have characterized this thing, then you must be saying a new definition of salt, which is a thing formed by the combination of acids and base. Suppose if I take NaCl, so that can be think of a combination of sodium hydroxide and hydrochloric acid. Similarly, Na2SO4 can be think of a combination of sodium hydroxide and sulfuric acid. So here is a example of the same, which is the formation of NaCl. It is formed by the reaction of the acid HCl and the base NaOH. So the cation and anion are coming from acid and base. Now if I ask you, which is the important part for anion? Means, is the base forming the anion of the salt or the acid? So if you look here, you can clearly say that the anion, which is Cl minus, is coming from your acid. It can be said for this above three examples also, which is NaCl, Na2SO4 and K2SO4, where the acidic part is contributing towards its anionic form. Next is a depth study of the salt dissolution in water. So we have taken the example of sodium chloride to understand the same. Suppose this is the picture depicting your dissociation. You can see that we have a NaCl cluster in the center and it is slowly decomposing into water, forming the various ions as Na plus and Cl minus. So what are the observations that you can see in the diagram? You can see a clear separation of the hydration, or you can say hydrated water molecules. Okay. Now, if you look into this diagram, you can note down some important informations. So those observations would be, first one is well separated due to hydration with water molecule. Means the ions of this NaCl is getting separated and it is happening due to hydration of this ions. Just look at this Cl minus ion. It is being hydrated with water molecules around it. So this is the basic meaning of hydration. It is a kind of association of water, right? What is the reason behind this association? The electrostatic force of attraction, because your chloride minus ion is having a negative sign and your water is a polar solvent. So the positive part of this water molecule, which is H, okay, that will get attracted to the Cl minus. As a result, all the H plus part of the water will be surrounding your Cl minus ion, and that will result in a hydrated chloride ion. Then if you look at the Na plus also, then what will be the atomic part of the water that will be attracted towards the Na plus? It will be your oxygen. Got it? So what can you say? That upon the dissolution of this NaCl, the force or the action that keeps your ions apart, the positively charged ions apart, is your hydration, right? So the hydration is the process that separates this ion or keep this ion apart from each other. Now next we'll move on to the Arrhenius definition of acid base. According to Arrhenius, acid is a substance which dissociates in water to give hydrogen ions. Whereas if you talk about the bases, then it is the species which donates OH minus ion. We can take example of acid. Here you can see we have taken a general example of acid as HX. This HX, when dissolved in water, it will give you H plus ion plus its anionic part. Then your next thing is your example. So HCl, H2SO4, HNO3. So all of these are examples of Arrhenius acids. Similarly, there is a very important part which you should remember, which is H plus stabilization. In the start of the lecture, I have said you that H plus is although formed in the start of any proton donation, but it is not stable. As soon as it is dissolved in water, it combines with water to form the H3O plus. Okay, and this H3O plus has a triangular pyramidal shape, which can be depicted in this diagram. You can see that oxygen is present on the top of this triangular pyramid, and the three triangular faces are being 3 H's with a positive sign on the top. Then if I talk about the base definition according to the Arrhenius, so these are those substances that dissociates into water to give hydroxide ion or OH minus ion. What about the example? So you can take MaOH as the general equation, as the general representation of this Arrhenius base, in which it is dissociating to give you a cationic part, which is M plus, and an anionic part, which is OH minus. So you will always see Arrhenius base donating OH minus. The examples of it would be NaOH, KOH, and calcium hydroxide. So all of these species will be dissociating in water to give you OH minus. Is it clear? Now remember a very important point. You must be noticing one thing for sure, that for a Arrhenius acid or base to work as acid or base, it must be dissolved in a water medium, or the acid and base should be present in aqueous solution. Then and then only you can define this acids and base according to Arrhenius, because at last they are being dissociated into two parts and they are hydrated in the presence of water. See, you can see a aqueous in the bracket of each of these species. Next is Bronsted-Lowry definition of acid and base. Now the acid part has a similar definition as to that of Arrhenius, means a proton donor is termed as acid. Example would be again the same one, HCl, H2SO4 and acetic acid. So all of these are donating H plus ion. But if I talk about Bronsted base, then rather than taking OH minus donor, he considered those species as base which accept H plus. Got it? So this is the difference between the Bronsted-Lowry definition of acid and base and the Arrhenius concept of acid and base. What can be the examples of it? We can take ammonia, F minus carbonate ion. So this all three will accept H plus. NH3 will go to NH4 plus, F minus will go to HF, and the carbonate ion will form HCO3 minus. We can understand the same with the help of one of this example, which is ammonia. See, when the ammonia is reacted with water, it is taking the H plus from water to form NH4 plus. At the same time, this thing is satisfying the Arrhenius concept because it is releasing OH minus ion in the water. But see students, in this case, we don't need water in every case, right? Because this H plus NH3 is accepting may come from any different solvent also or any different acid also, right? So what are the observations in this diagram? The first is the basic solution forms when the NH3 accepts your H plus. This releases the ammonium ion and the hydroxide ion. The second thing is that, which is very important and a very interesting part also, is the action of water. The water is donating a proton, so you can say that it is acting as an acid in this particular reaction. And the last one is that if you see the reverse part, because this ammonia is a weak acid. Why is it a weak acid? Can you look at the equation and say that it is a weak acid? Yes, because it has a double-headed arrow here, double hooked arrow oriented in opposite side. That means this reaction is for a weak electrolyte, or you can say it is for a weak base, which is ammonia. Now in the backward reaction, what will happen? Say in the backward reaction, this OH minus will accept the hydrogen and form the H2O. Got it? The last point is ammonia is acting here as a Lowry-Bronsted base. Why? Because it is accepting H plus in this reaction. So your H2O is acting as a Lowry-Bronsted acid and ammonia is acting as a Lowry-Bronsted base. Next is the most important discussion of these three concepts included, which is conjugate acid and base. So this is very, very important to understand. You can consider the same example for understanding this conjugate acid and base. So we have taken this reaction of ammonia with water. Then in this reaction, if you want to know that what is your conjugate acid base or what is your conjugate acid base pair, then how would you decide it? So the acids and base that differ only by a proton are termed as acid base pair. For example, if you take NH3 and NH4 plus, the only difference between these two spaces is that NH3 has taken up one H plus to form a NH4 plus. So the difference is of one proton. So what you can say that this ammonia and this ammonium ion are conjugate acid base pair, in which the base is acted by, the basic part is acted by the ammonia, where the acid part is played by the ammonium ion, because NH3 is accepting the H plus and NH4 plus is donating the H plus. Is it clear? So this is very, very important to understand. Then if I talk about the second participant of this reaction, it is water, then water here is acting as a proton donor. So this is a base. And what would be its conjugate base? It would be OH minus, which is formed by decrease of one H plus. So they are only again differing by one proton here. So a very important point to discuss, which I will tell you, is that the strong acid have a weak conjugate base. So what can you arrive from here? So if this ammonia is considered as your base, then its conjugate acid is NH4 plus. If I ask you that which one is strong and which one is weak, how you will decide it? So if it is a strong base, then it will form a weak acid, right? First thing. And if ammonia is a weak base, then it will form a strong acid, right? I have told you in the start that ammonia is a weaker base because it is not dissociating completely to form your required ion. So therefore, its conjugate acid will be a strong one. Got it? Whereas if you talk about the strong base part, that has the same story. So a strong acid will have a weak conjugate base and a strong base will have a weak conjugate acid. Moving on to the next, which is amphoteric nature of water. What is the meaning of this? So you have seen water in the previous reaction acting as an acid. But this substance has a very unique nature of acting as both acid and base. So we called your water as amphoteric because amphoteric is the definition for those substances that can act both as acid and base. We can take some examples. So if I take for the acidic nature, we can take your ammonia and water reaction again, where the water is donating your proton to the ammonia to form the ammonium ion, and itself it is getting reduced to the hydroxide, which is a conjugate base of the acid. Then the next part which is played by the water in this reaction is base. So here we are taking a stronger acid, right? So ammonia is a weaker acid than water, or you can say it is a stronger base than water. So both are true. Second thing, if you see, then HCl is what? HCl is a strong acid than water, right? And weaker base than water. That is the reason here water is acting as a base and your HCl is acting as acid. After the reaction, the HCl loses one proton to form the H3O plus for water and itself get reduced to the chloride ion. Now if I ask you, what is the conjugate base of this HCl acid? You will tell it as Cl minus. Similarly, the conjugate acid of the water is H3O plus. Here's a question for you. We have some species given here. You have to see that for each species, what is the conjugate acid and what is the conjugate base. So let's see how can we solve it. So first, you know that conjugate acid and base differ only by one proton. If I talk about base, if you have to find the conjugate acid, if I talk about base, then the base will take a proton to form the conjugate acid. And if you have to form a base, then the acid will give up one proton to form the conjugate base. Now, based on these three important informations, the following table can be built. You can see we have our four species: water, HCO3 minus and HSO4 minus and ammonia. If water takes up one proton, or you can say it acts as a It acts as a base, then the corresponding conjugate acid H3O plus is formed. Whereas on losing one proton, the conjugate base is formed, because here in the second part the water is acting as an acid. Now if you move on to the second one, which is HCO3 minus, then this species can be converted into conjugate acid by accepting one proton to form the H2CO3. Whereas if you remove one proton, then it will be converted into CO3 2 minus. So here it is acting as acid. If I ask you, how would your HSO4 minus act as a base? Third one, when it will accept one proton and the resulting one would be its conjugate acid. In the place of that, if it is donating one H plus ion, then it will form SO4 2 minus. Got it? Similarly, you can do the same for ammonia and ammonium ion and your amide. Now I am giving you a homework. Just try to write the equation for each of this and see whether the proton transfer is occurring or not. Just try to analyze these four options. Now moving on to the last definition, which is the Lewis definition of acid and base. According to this, the acid are the substances which accepts electron pair. So this was a totally new dimension, right? This was a totally new dimension where your acid was accepting an electron pair. Rather than proton and hydroxide, we are now interested in electron pair. Now, if I ask you which substance will accept your electron, so the obvious answer would be electron deficient species would accept electron. So based on this idea, we can take example of BF3 or AlCl3 H plus and CO2 plus. First, what about cations? So the thing is very obvious, since they are cations, they are lacking in electrons, so they will accept that. If I talk about this AlCl3 and BF3, then what is the reason behind its electron acceptance? So the reason for this two are, they are electron deficient because they don't have their octet complete. If you count the total number of electrons of boron, including its valence electron and the electron coming from fluorine, then it will be counted on to 6, which is less than 8. Similarly, your aluminium has the same aspect where it is having only 6 electrons, and that is the reason it will act as an electron acceptor. Moving on to the base, the opposite of electron acceptor, base acts as an electron donor, according to Lewis. Now, the same logic would be applied here also. The species with a abundance of electron or an excess of electron will be available for donation. Like, if you talk about this negatively charged ions, then you will say that okay, the charge is more, negative charge is more, so they have an excess of electrons, so it will donate. But what about this NH3 and H2O? How are we saying that they are electron donator? Because all of these two are having lone pair on the central atom, not central ion, central atom. So ammonia has one lone pair and water has two lone pair, and that is the reason they are classified as Lewis base, because they can donate their lone pair during acid-base reaction. We can represent both acid and base in a single example. Suppose we have taken ammonia and your BF3, boron trifluoride. Here your ammonia is donating electron, so it is acting as a Lewis base, and the BF3 is accepting those lone pairs, which is electron deficient in nature. So here the boron for trifluoride is acting as Lewis acid. After reaction, they form a dipolar species having both positive and negative part. This thing is also termed sometimes as adduct. In this reaction, your adduct is represented by BF3, then we have an arrow, then we have lone pair and NH3. If I ask you, what is the hybridization of ammonia after the reaction, or the nitrogen, I would say after the reaction, not ammonia. The nitrogen is still sp3 hybridized, only in the place of lone pair now we have a bond. So here your BF3 is accepting the electron, so it is a Lewis acid, whereas your ammonia is donating the electron, so it is a Lewis base. Now we'll do a question. So you have to divide this given species into Lewis acid and bases based on the tendency of their electron acceptancy and electron donation. So how you will do it? It's very simple, I guess. So for the negative and positive charge, you don't have to think much. If it is having a negative charge, it has excess of electron, like in the case of OH minus, so it will donate electron and hence act as a Lewis base. Similarly, the fluoride ion also has excess electron, which is significantly represented by the negative charge, so it will again donate electron and act as a Lewis base. But the H plus will act as an acid because it has a positive charge and has a tendency to accept electron because of the electron deficiency. But what about BCl3? Similar to boron trifluoride, it will also have a sextate or an incomplete octet. As a result, it will accept electron and hence act as a Lewis acid, like your boron trifluoride. Again, if I ask you what are the species that can donate electron, you can take the ammonia or your amine molecule as a base for this Lewis acid. So we can summarize our today's lecture. First of all, we saw ionic equilibrium. It is that state where your dissociated and undissociated part have what? They have a equal concentration because the rate of dissociation equal to the rate of association. After that, we saw Arrhenius concept where he said that the species which donate H plus are termed as acids and the species which donates OH minus are termed as base, and this can only be applied to the aqueous system. After that, we saw the Bronsted-Lowry concept, according to which acids are substances which donate H+, whereas the bases are substances which accept this H+. This was much more broader as compared to this Arrhenius. Moving on to the last concept of acid and base was Lewis. So its definition was not on the basis of any ion. Rather than that, he concluded electrons. He said that acids are substances which accepts electron and bases donates electron. You will always remember the cations are always electron acceptor and hence acids, whereas the anions are always electron donators and hence bases. If they are not ions, we will take the case of deficiency, whereas we have this in the case of base, we have the lone pair on the central metal ion. Is it clear? So this was all for today's lecture. Thank you for attending the session. I hope you enjoyed it.